Hey, welcome back. Today, we're going to tackle one of the most powerful ideas out there, Bayes' theorem. Now, I know it sounds kind of nerdy, but trust me, it's more than just a stats thing. It is an amazing tool that can literally help every single one of us think more clearly and, well, update our beliefs when we get new information. And to show you just how powerful it is, we're going to start with a little puzzle.
Okay, so picture this. There's a test for a rare type of cancer, and this test is 99% accurate. You go in, you take the test, and it comes back positive. So here's the million-dollar question. What's the probability you actually have the disease? Now, your gut instinct is probably screaming 99%, right? I mean, that seems obvious. But what if I told you that's not even close?
Get this, the actual probability is only about 9%. Yeah, 9%. Isn't that wild? You have a 99% accurate test, you get a positive result, and there's still a 91% chance that it's just a false alarm. How is that even possible?
This crazy result, this apparent paradox, is exactly what we are going to solve today. It feels like a trick question, but I promise you it's not. It's just a perfect example of why our brains need a better way to think about probability. And to unravel this whole mystery, we need to start with this idea of thinking in conditions.
You see, the whole reason our intuition gets so tangled up here is because of a concept called conditional probability. Basically, we're always mixing up two very different questions without even knowing it. This is all about how we should adjust our predictions about one thing once we get new information about something else.
So, in the world of probability, there's a special way to write this. P of A given B. You just read it as the probability of A given B. Think of it like this. Normally, you're looking at all the possibilities in the whole wide world. But with conditional probability, you're zooming in. You're saying, okay, let's just pretend we are in a world where we know B is true. Now, in this new, smaller world, what are the chances of A?
And this, right here, this is the absolute heart of the confusion. That 99% accuracy number, that's telling us the probability of testing positive given you have the disease. That's the forward problem. It's how they design and test the test. It's easy to measure. But that is not what we care about as the patient, right? No, we want to know the inverse. What's the probability we have the disease given we tested positive? That's the real question, and it's the harder one to answer.
So, how do we flip that around? How do we get from the probability the test knows to the probability that we want to know? Well, this, my friends, is where the magic of Bayes' theorem comes in. It is the mathematical key that lets us solve this exact kind of inverse problem. So, here it is in all its mathematical glory. And I know, it might look a little intimidating with all the letters and the brackets, but I promise you the idea behind it is incredibly simple and intuitive. In fact, we can just translate this whole thing into plain English. Let's just break this down. The posterior, that's just a fancy word for your new, updated belief. You get it by taking your prior belief, what you thought before you saw the evidence, and multiplying it by the update, which is basically the strength of that new evidence. And that thing on the bottom, that's just a bit of math to make sure our final answer is a proper percentage. See? At its heart, the formula is just a really structured way to change your mind when you learn something new.
Okay, so now we have all the pieces we need. We've got the framework. Let's go back to our medical mystery and use this formula to see exactly how we end up with that shocking 9% answer. So here are all the numbers from our problem, laid out nice and clear. The test accuracy, the true positive rate, is 99%, which means the false positive rate is 1%. But here's the crucial number, the one our intuition completely ignores. The disease is super rare. Only 0.1% of people have it. That's just 1 in 1,000. This is our starting point. This is our prior belief.
Now we can just map these numbers right onto our belief updating formula. Our prior belief of having the disease is that tiny number, 0.001. The update from our positive test result is 0.99. And, critically, we also have to account for the chance of a false positive, which is 1% of the 99.9% of people who don't have the disease.
So when we plug these values into the formula, you can really start to see what's happening. The top part of the fraction represents the people who have the disease and correctly test positive. But the bottom part of the fraction, that represents everyone who tests positive. That includes the true positives and the false positives from that much, much larger group of healthy people.
And boom, there it is, about 9%.
The number of healthy people getting false positives is so large that it just completely swamps the number of sick people getting true positives. So think of it this way. Even though your positive test made you 90 times more likely to have the disease than the average person, your starting probability was so incredibly low that your new updated belief is still only 9%.
And this isn't just some neat brain teaser. This exact principle applies absolutely everywhere, from courtrooms to how your spam filter works. To really drive the point home, let's look at another classic example: workplace drug testing.
Okay, new scenario. A company uses a drug test that's 90% accurate both for users and non-users. We happen to know that 10% of the population are users. An employee takes the test, and it comes back positive. So what's the actual probability they're a user?
If you run the numbers through Bayes' theorem again, the answer is only 50%. A positive test is literally no better than a coin flip. And now look what happens if the test's false positive rate gets just a little worse, going from 10% to 20%. All of a sudden, the probability that a positive test means a real user just plummets from 50% all the way down to 33%. The accuracy for non-users is just as important as the accuracy for users.
So, what this all comes down to is that our intuition gets fooled. We tend to fixate on that one flashy piece of evidence, like a test's accuracy, and we totally ignore the other crucial context. Bayes' theorem is the tool that forces us to account for that starting probability, what we call the base rate, and the very real possibility of false alarms.
And that leaves us with a final thought to take into our own lives. We are constantly bombarded with these dramatic, vivid stories, right? A shark attack on the news, a friend of a friend who won the lottery. These things feel so important, but they are almost always incredibly rare. So the question is this: what's a common belief you hold that might totally change if you actually stopped and considered the real base rate?